Welcome back! In this lecture we'll be discussing mole, molar mass, and how to balance a chemical equation. We see the element silicon here, as it would appear on the periodic table. As you can immediately see, there are 14 protons in the nucleus of a silicon atom. Its atomic mass is apparently 28.09. But how is this atomic mass calculated? Well, an element is defined by its number of protons, the number of neutrons in the nucleus can vary. Atoms with the same number of protons but with a different number of neutrons in the core are called isotopes. And often, one element has multiple stable isotopes that occur in nature. And this always happens according to the same ratio. You can see this for silicon in the cutout from the chart of nuclides shown on top of this slide. There are 3 different isotopes of silicon with either 14, 15, or 16 neutrons in the nucleus. The isotope that is found most in nature is silicon-28. 92% of all silicon is this specific isotope. We call this the natural abundance of the isotope. The average atomic mass can be calculated as the weighted average of the atomic masses of all naturally occurring isotopes of an element. And we use the atomic mass unit U to talk about the mass of an atom. One atomic mass unit equals 1.66 times 10 to the negative 27 kilograms, and it's defined as 1/12 of the mass of a carbon-12 atom. We can calculate the average atomic mass of any element, like silicon, by multiplying the mass of the different isotopes by its natural abundance. And that is exactly what you see displayed on the periodic table for each element. Now, if we look at molecules, for example silicon dioxide, we can calculate its molecular mass simply by adding the atomic masses of the different atoms. But remember, we're still talking about the mass of just a single atom or molecule. In practice, we always encounter extremely large amounts of molecules. Just think about the number of silicon dioxide molecules in the glass windows in your house. You can imagine that it's not practical at all to talk about the amount of single molecules in a solid or a solution, and that is why a new unit was invented, the mole. The mole is the unit we use to measure the amount of a substance, and it's defined as exactly 6.022 times 10 to the 23 particles. The molar mass of a substance is the amount of grams per mole of that substance. And as you can see, it's numerically the same as the molecular mass, but it has different units, grams per mole instead of the atomic mass units. The molar mass is very convenient if you want to convert moles to grams, or the other way around. For example, if you know you have 2 moles of silicon oxide, you can calculate its mass by multiplying it with the molar mass. All these atoms and molecules can exist in different states, and we call these the states of matter. When the particles are solid, they are tightly packed together. And in liquids, the particles have more movement, while in gases they are much more spread out. There are different types of solids. If a solid consists only of metal atoms, we call it a metal. We call something a salt when it contains metal and no metal atoms. And a network solid, such as diamond, consists of solids that are held together by covalent bonds. And molecular solids are held together by van der Waals forces. If you take a solid, like for example a salt such as sodium chloride, and put it in a solution such as water, the salt can dissolve. The solution that is formed contains sodium ions and chloride ions. We call the number of moles of this solute that is dissolved in 1 liter of solution the molarity of the solution. The units of molarity are, not surprisingly, mole per liter. This example shows you how you can calculate the molarity of a solution when you know the molar mass of the molecule, the number of grams you are dissolving, and the volume of the solution you are dissolving it in. Just like any chemical process, we can represent the process that we just described, the dissolution of sodium chloride in water, by a chemical equation. Let's use the chemical equation of the production of ethylene from carbon dioxide to show how to write and balance such a chemical equation. First, we write the equation in this form, with reactants, in this case carbon dioxide and water, to the left of the arrow, and the formed products, ethylene and oxygen, to the right. Then we need to balance the equation. In every chemical reaction, the number of atoms and charge is conserved. This means that the same number of carbon atoms need to be on the left and right-hand side of the arrow. Because ethylene, the product, has 2 carbon atoms, there also need to be 2 carbon atoms on the side of the reactants. That means that, in this reaction, 2 carbon dioxide molecules need to react with 2 water atoms to form the required ethylene. Counting up the total number of oxygen atoms at the reactant side yields 6. So we balance the equation by having 3 oxygen molecules being produced at the product side. And finally, don't forget to include the states of matter. In other words, were the molecules that were reacting or being produced in the solid, liquid, aqueous, or gas phase. In this lecture, we have seen how to create some balance in the sea of molecules. We'll take a closer look at a special type of reactions, redox reactions, in the next lecture.